want to make sure you all hear me. Is it okay with the speakers and everything? It's cool? All right. Oh, GW17, which you guys are all experts on by now, the binary neutron star merger, and as well as the related gamma ray burst GRB 17. From these, you'll notice that astronomers are not very creative in naming their. What happens to transients is name things month and then day. And things like A, because sometimes you have multiple GRBs in one day. Fun though. So for at some point we started going with A, B, C, etc., just lettering things GRBs that happen in one day. But it's not in order of when the GRBs are detected, but in order of when their circulars are written. So when the GCN circulars are written. So sometimes A actually happened after B. So this is all kind of silly. So, oh yeah, one question was, is there anything going to change in the future with naming things, or sorry, with GRB and sort of GW detections and things like that? One of these things is we're maybe going to figure out better naming schemes. And this is also relevant for gravitational waves because right now we have one per month, couple of months, maybe a couple in a month, never multiple in a day. But at some point, we're going to have multiple gravitational wave detections in one day as well. Kind of interesting. It's kind of fun. The to learn from the community. So now, yay, we finally directly detected gravitational waves. So these are some diagrams. These are some of the signals from previously detected binary black hole mergers, or BBHs. These are the first 5 detected by LIGO. Actually, if you noticed recently, there's been an update, and now there are 10 total binary merger detection. There's now a new LIGO transient catalog. That's all open and public and everything. So if you want to take a look, there's a new catalog, and we've detected a couple of more, or found a couple of more events. This is because, if you take the original data and you do the best you can with it and then when you have some more time, you go back to it later, maybe with better calibration of your detector or some more different waveform models or more models of how the signal looks like, and then you could pick out signals that you couldn't before. So we have all of these BBH detections, and the longest signal, so this is just the waveform when it's detectable by LIGO, right? Because this is the very end of the INSPIRE merger. The two events were obviously, the two black holes were obviously inspiraling for a long time before that. This is approximately when it enters the LIGO frequency band. Now you have the neutron star, and it goes for a lot longer, right? So all the black holes lasted, let's see, the signal lasted for less than 2 seconds, and LIGO's frequency band, the neutron star merger, lasted for almost a minute. I should say specifically, when we say what LIGO's detected, we talk about detecting the merger of binary black holes, because we actually detect the final moment the two merge, or as best as we can. Technically, we've only detected the in-spiral of the two neutron stars. This is because when the neutron stars finally merge, it's at a much higher frequency. It's at a higher frequency that's slightly outside of LIGO's band. So technically, we haven't detected the merger neutron stars. We've detected the in-spiral neutron stars. I was corrected a couple of times in the past by various binary coalescence colleagues, so just want to make that clear. So this is very exciting. This led to the paper with, I think, maybe the longest list of collaborations. It's not actually the most number of authors, because I think part has thousands and thousands of people on author lists. So this is maybe 1,500 authors. Kind of heartwarming when you see the you see LIGO and Vero on there. You see the gravitational wave detectors. You see Fermi, GBM. You see integral. So you see some X-ray, gamma detectors, or just gamma ray detectors. You also see things like IceCube and Antares, which are neutrino detectors. We haven't detected neutrinos yet, but we're hoping one day we will, maybe. It's kind of exciting to see all these different and all these different data types working together. I can also tell you, though, that this was I was to some of the, or I was around when some of these discussions were going on. It's really hard to coordinate this number of authors, right? But somehow it got done. And so, yeah, so this paper is online. I think it's also open source free. So what actually happened in gravitational waves? Let's see. There are two light detectors, Hanford and Livingston. At the time, in general, Hanford was having some issues with some of its machinery, so it was slightly less sensitive than Livingston was. So Livingston was more sensitive. Livingston should have detected something automatically because it was pretty bright. And you can see in here, actually. So what you're seeing here are frequency versus time. At the top is Hanford, the middle is Livingston, at the bottom is Virgo. And so you can see it's brighter in Livingston, right? You can see that track much better in Livingston. So there was more power deposited in Livingston. Livingston was more sensitive at the top. Here's the problem. Hanford reported an automatic detection, right? Because all these detection algorithms are running in real time. Hanford gave an automatic detection notice. Livingston did not, because it turns out there was a glitch, some sort of instrumental disturbance right in the middle of this lovely signal in Livingston. So that's part of what caused some of later the timeline of events. There was a little bit of delay. We first had to subtract out I didn't do anything. LIGO, the people who were involved in doing this analysis first had to subtract out the glitch or the instrumental disturbance from Livingston before they could get better information on where the event came from and things like that. So this was pretty bright in Livingston, or pretty loud, because we're talking about gravitational waves, we talk about loudness, not brightness. This is pretty loud in Livingston and Hanford, very high signal to noise ratio. It was loud enough that it should be detected by Virgo as well. Virgo did not see anything, actually. This really helped, because the detectors are kind of like this, they're L-shaped, right? The detectors, the way they are, they're sensitive, they're more or less sensitive to different parts of the sky. Each of these detectors has kind of a blind where it's the least sensitive. And so because it did not detect anything when we expected it would have, just based on loudness alone, that it must have been a Virgo blind spot at the time. So that actually really helped localization. And it got things down from like thousands of square degrees in the sky to a much smaller, much narrower range. So what we're looking at here are some of the localization contours. If you take, you take Hanford and Livingston by itself, you basically get two large bananas in the sky. Oh, sorry, this is only hundreds of square degrees. Yeah, so you get two large bananas in the sky. So that's the light blue contours, and then add in, rapidly, right? This has to be rapid because everything's fading. And everything is fading, the afterglow, the kilonova, if it exists, might also be fading at this time. And so therefore, things out really rapidly. That also means maybe because analyses can take a while, maybe you don't use your best analysis methods, you use your low latency or sort of rapid analysis methods, and that gets you this blue, this inset, this sort of dark blue contour right here. And then after a little bit more time had passed, and you sort of time, crunch the numbers on your computers or on registers to really get the best localization possible, and that actually shifted the localization contour a little bit to this green down here. And not only do you get sort of this 2D localization, where is it in the sky, so you also get the 3D localization of where it's coming from, how far away. I just realized this is probably, nope, this is not all right. Okay, so this is another just illustration or visualization of where things are in the sky, where you have the Milky Way galaxy, the plane of the Milky Way, kind of horizontal, and then you have these error circles, and this just shows you what happens when you have multiple sets of detectors. So when you only have two detectors, you have this one great ring in the sky, and then when you have all these sets of two detectors at a time, then you can sort of see where do they all overlap. Where they all overlap is where you're going to get your best localization. Just to show you kind of what happens, it gets, why, or just a demonstration of how localization gets a lot better when you have 2 versus 3 detectors detecting something. For most of these events, we only had the 2 LIGO detectors working. For 1708-14, so this was an interesting time actually. 3 days before the BNS, we had detection. So 1708-14 is something that was detected by both LIGO and Virgo, and so that's why it has a much smaller localization on the sky, and then 1708-17, because it's been detected by 3 instruments, also a much smaller localization on the sky, whereas a lot of the other ones have sort of these wide rings on the sky. And I think 1509-14, which was the very first detection, that has a relatively small one, I think simply because the signal to noise ratio was a lot larger. And so you had basically the signal was a lot more significant, and so you could see it a lot better, you could characterize it a lot better, so you could localize it a lot better. All right, so you detect, most of the time, you detect these mergers, coalescences, or inspires because you have a bunch of waveforms. So these waveforms, these signal waveforms come from GR, and you have the data, and it's kind of messy and spiky and stuff, but then you say, let's take a look at this portion of data, and let's try to compare this data to all of our waveforms that we have that we expect we might be able to detect. And you say, all right, there's a subset of waveforms, so a series of waveforms that all more or less fit the data well, explain the data well. And so when you do that, and then you say, you go back and you say, all right, what subset of waveforms explains the data well? And when they did, they said, well, it's a set of waveforms where the two masses, the total mass is around 2.74 masses, where the individual masses are in either this range or this range. And so what you're seeing here on the plot on the left is, on the horizontal is the mass of the primary object, that's defined to be the heavier one, and the secondary object, again, just defined to be the lighter one. Of contours here are two sets of histograms and sort of lines here, because when you're doing all of this, you have to make some assumptions about, for instance, how fast the objects are spinning. Depending on how fast they're spinning, as well as other things, you have to make assumptions about how fast they're spinning, the spins we're at, how the waveform changes a little bit, whether things are sort of processing, whether everything is sort of moving around a little bit, the angular momentum of the entire system is moving around a little bit. So all of these are going to change what waveforms explain, or what systems explain the signal the best. So what you're seeing in the red here is, this is when you make no assumptions about spin. You say, here's a neutron star, it could be spinning unrealistically fast. Depending on who you ask, it's unrealistic. When you say it could be spinning incredibly fast, that can be a very are possible masses for these neutron stars. But you could also say, well, the spin's probably not very fast. This is sort of, I think, from both physical modeling as well as from sort of observations and things. And then when you do that, you constrain the masses up better. So what you're seeing on the left is a plot from the initial detection paper. This just came out a couple months after the event. And on the right, this is a very recent paper. And the recent paper, what happens is you see there's sort of four sets of kind of these histograms on here. And this is because with the recent paper, they've looked at, these are all just different waveforms. So different ways of modeling the final waveform. And they each give you some slightly different signal shapes, basically. So from there, they'll give you, or for the most part, they're all consistent with each other. And then you can do things like well, how squishy versus how compact and hard are neutron stars, or in these neutron stars in particular. So on the x and y axis, so again, for both of these, the horizontal axis is the primary neutron star, so the vertical axis is for the secondary neutron star, the less massive. What you're seeing are the stability, which is essentially how stretched out how easy is it to stretch these neutron stars. These are, let's see, and again, on the left, this is the initial detection paper. On the right, this is the more detailed study that came out recently. It's still in the archive. So on the left, let's see. Yeah, so on the left, you see this sort of dotted line. There's a 90% contour and there's a 50% contour. What this is saying, actual tidal deformability parameters lie somewhere in this bottom left range here. We're 90% sure it lies in this range over here. And larger, when you go farther to the right and farther up, that means the neutron stars are sort of squishier, or can expand more, they can change, they can deform shape a lot more. And so from the top right is less compact. When you get to the bottom left, that's more compact. And these contours, these sort of curves over here, these are for different equations of states. So these are different, starting from different models of neutron star interior. Different models will predict kind of different combinations of tidal deformability parameters. What this is saying is that anything So you see this dotted line again, the 90% dotted line. Any equation of state that gives you something to the right of that is less likely to actually be true, I guess, or to actually hold than anything to the left of that. And so that's what you do. That's one thing you can do to try to figure out what the equation of state is. On the right-hand side, it's something similar. It's just slightly more detailed study, again, using different types of waveforms or ways of calculating the waveforms. So here we have just a combination of the gravitational wave detection as well as the GRB. What you have in the middle is the gravitational wave detection. This is, what's sometimes known as chirp, because as you go farther up, it gets higher in frequency, so the pitch kind of goes up. Then on the top, you have what's the light curve, so the gamma rays that were detected by the Fermi spacecraft. And then on the bottom, you have the gamma rays detected by another spacecraft, integral. And in both cases, you see the gamma rays really peak around 2 seconds after the gravitational. And so one of the questions causing that, how does that constrain models, right? Because what's happening is you have the two neutron stars merging, and at the merger, they produce the gravitational wave chirp. And then at some point, right, we're talking about, then they produce a jet, and things propagate. The jet moves, the jet propagates, the jet sort of slows down, and then at some point we detect gamma rays. And so this starts to help you constrain models for how the gamma rays come out of, let's say, neutron star mergers. So about the Fermi Gamma Ray Space Telescope. So there are two instruments, and the main instrument actually is the Large Area Telescope, or LAT. It's this big metal box that's on top. So this is higher energy, and this is a pair production. What that means is layers. You have these layers of very heavy material, very high atomic number material. So, and then you have these layers in here, and then in between there's these kind of silicon strip detectors. Basically, they can detect when charged particles go through. So what happens is the gamma comes in and it interacts with high Z material. So in this case, it's tungsten, right? It's a relatively dense material. It comes in and it interacts with the tungsten around its electric potential, and then interacts with them. It pair produces. It converts into an electron-positron pair. When it converts into the electron-positron pair, then the two charged particles kind of go through the silicon strip detectors. When they go through, they leave holes in the detectors. Not technical holes, right? But you can track how the charges move in the detectors. When the charges move, then you say, all right, well, the electron-positron pairs, it went like this. And so you kind of work backwards and you say, then the original gamma ray must have come from over there. The LAT, so that's how the LAT works. That's kind of zeroth order understanding, because really what happens is you get one charged particles, and then these are still pretty high energy, so then you get a particle cascade, right? So it's a little bit more complicated than that. But essentially, by figuring out where the charged particles, what direction they came in, you work backwards to figure out where the original photon came from, and also how much energy it had. Then there's the gamma ray burst monitor, and that's the GBM, and that's sort of more slightly relevant for what we're talking about here. It's because it's a lower energy range, and it's an energy range that's really good for GRBs. The GBM detects about 1 GRB every 2 days or so. % of the GBM's. This was a little bit unexpected because before Fermi launched, we knew the spectrum looked sort of like this. Before Fermi launched, we knew the spectrum kind of looked like this, but then it was like, so we knew it kind of looked like this, but then it was like, where does it peak? Where does it turn over? Does it keep going over? Does it, drop really quickly? And so the expectations were, if it just kept going and sort of then dropped slowly, we should be getting a lot more LAT GRBs. We should be getting, let's say, GBM GRBs having LAT emission. That is higher energy. And then it turns out that only about 10% have this. And so this is kind of a new thing where we found out with everything combined that the turnover is actually a lot lower than we thought. And that sometimes there's actually even a cutoff, maybe because particles are, maybe because the regions are really dense and other particles are getting in the way, and so you don't actually the highest energy particles anymore, or the highest energy photons. Anyway, yes. It's actually of detectors. It's 12 detectors, sodium iodide detectors, and 2 bismuth germanate detectors. Basically, 12 detectors are lower energy, slightly lower energy, and the 2 BGO are slightly higher energy. Detectors, the 12 NAI detectors are positioned on the 2 sides of the spacecraft. So basically on this side of the spacecraft you have 6 detectors, on this side you have 6. With this set of 6 detectors you also have a BGO. With this set of 6 detectors you have a BGO. These detectors count photons, count rates. Each NAI detector on its own cannot tell you exactly where in the sky things came from. But what you do is say, well, if this detector over here is detecting a much higher rate than these, and you know how well detectors will detect, and you know your detector responds from different parts of the sky, you work backwards and say that the GRB must have been coming from this position or from this position. The other relevant detector here, which I'm going to talk about, but there's Integral, or the International Gamma Ray Astrophysics Laboratory. There, that's on board. I actually don't know exactly. More relevant for me is that the anti-coincidence shield around it. What's the anti-coincidence shield? Why do we need it? So going back to the lat layers of material that converts photons to charged particles. What happens if a charged particle enters the lat in the first place? Right? That's sort of your background. Detect photons, detect high energy rays. You have a very strong charged particle background. Particles are produced. Also, will get these tracks going through your detector. And so what you need is a get rid of that charged particle background. And I think the rate of charged particles is like 29. No, it's 3 orders of magnitude higher than the rate of your background is really high, and you get rid of it really well. So what you do is you put a detector around, let's say, your primary instrument. And so, if you see, so what you do is you say, okay, something came in. I know something came in and produced a track. Is it a gamma ray or a charged particle? If it lights up the shield around it, the anti-coincidence shield around it, then it was a charged particle. And that helps you. And then from there, you can sort of throw that event away and you say that was. If it doesn't light up that shield, it was a gamma ray, and you keep that event. So something similar happens or lives around the spectrometer for Integral called the anti-coincidence shield. So it also detects charged particles, and it also manages to detect gamma rays as well, because again, gamma rays are just one conversion event away from being charged particles. And there's no direction or energy information from it. It only counts rates. All of this is important because some like this that have a lot of stuff on them, and these kind of show you where things are. So what you're seeing, that's the part of the sky that's obscured by the Earth. Let's see, I think this is in the point of view of the GBM. Yeah, I think this is based on where the GBM was. Part of the sky is just obscured by the Earth, so there's nothing that it can see from there. In the smaller insets, the green contours are the gravitational wave only contours, so the sort of small bananas we saw before. And then the purple is the GBM only localization contours. This gray blob, this gray line, what that is the other instrument, Integral, the other instrument that detected this, it cannot actually localize where gamma ray burst was coming from. But what you can do is say, GBM is over here, and it detected it at this time. Integral was over here, it detected it at this time. You work backwards, and you triangulate, and you say, based on those 2 differences in the time of arrival, it must have come from somewhere in this part of the sky. And so that's how you get this sort of long blob. So you can start to do interesting physics just by looking at the light curves. Because what happens is we have photons and we have gravitational waves arriving at the same time. And we expect, they should travel at the same speed, but there are plenty of models and plenty of theories that say at some point this assumption breaks down. So what we know, GRB started about 1.7 seconds after the merger. We know when the merger occurred, and we know when we first observed GRB photons. So if the GRB photons were released a little bit after the merger, so some delay there, caused by, like I said, the time for the jet to form and propagate in the first place to release those photons. There's also there's a different travel time for photons or gravitational waves. So what do you do here? You can make an assumption here to constrain the difference in the speed of gravity and the speed of I'm going to assume time. If they're emitted at exactly the same time, then you have an upper bound on the difference between the speed of light and the speed of gravity. At the same time, and then we detected the light a little bit later, that means gravitational waves travel a little bit faster than light. Physically, not necessarily true, but this is, depending on who you ask, but this is a way to start to constrain things. And you notice that the constraint is as good as 1 part in 10 to the negative 16 or 15 or so. So this is a very precise constraint. I think this is the most precise constraint we have. On the other hand, we can say, all right, we know it takes a little while after the merger for the jet to form and propagate before it releases gamma rays. So the gamma rays were actually emitted about 10 seconds after the gravitational waves. So here it's a little bit more sort of hazy, right? But what you do is you have some assumption about how long it takes, some reasonable assumption about how long it takes to get those gamma rays out. And if you say it takes about 10 seconds, all right, so if it takes the gamma rays about 10 seconds for the merger to come out, but now we detect them about 2 seconds before, then the gamma rays must be traveling a little bit faster than the gravitational waves, and from there you get this other constraint on the other side. Yeah, we talked about this a bit yesterday, but it was kind of unexpected. This GRB was in some ways was normal. It was really unexpected because you would expect bright flashing gamma rays with fading, let's say, X-ray emission. But in reality, was something a little bit different. At the top, what you're seeing is the GBM detection where you see all these sort of fluctuations. So this is the counts per second, so this is how bright it is over time. This is just what the detector saw. And you see all these little fluctuations around the background. And then the actual detection, the actual GRB, is not that much brighter than the background fluctuations, right? It's not that much taller. So this is pretty dim. And then what you see at the bottom, these are different afterglows. So in the black, these are the X-ray afterglows of long GRBs. They sort of span this kind of black, dark gray region. In the blue are the X-ray afterglows of short GRBs. So these are the different lines. What you're seeing in the green down here, most of these are arrows. So most of these are upper limits. This means that telescopes looked for it and didn't see it. They looked for it, and they could set the limits to be much lower than any other previously detected short GRB afterglow limits. If we go back and we focus on the prompt emission, what you're seeing on the right is a distribution of the histogram of the peak brightness or the peak flux of short GRBs, and in the solid histogram, you see in the green and the orange region, that is the peak flux of 1708, 17A of GRB, which is weird. GRB on average this GRB was a lot closer than the rest of the GRBs, and yet it was so much dimmer on average than the other GRBs. See, left here is a plot of the luminosity, another sort of measure of brightness against redshift for different kinds of GRBs. And what you're seeing is that even though 1708, 17A, which is this purple star over here, was so much closer, it was also really dim, or really low luminosity, low energy. The other weird thing about the afterglow, so because it's so close, you would expect the X-ray afterglow to be relatively well detectable. It should be relatively brighter for us to observe because it's just so close. But again, instead, it wasn't detected. It wasn't detected until about 10 days later. When it was detected, it didn't decay. You would expect the X-ray afterglow to just kind of fade away at this point, but instead the 3 dots were kind of really close to each other in sort of brightness. And so how do we explain the combination of these behaviors? You explain basically by the fact that we're viewing it really off axis. So this is from the gravitational wave detection. So from the gravitational wave, less than about in the fact that we figured out, so NGC 4993 is the host galaxy. When you add in the fact that we know the host galaxies over there, then you really constrain the angle to be less than about 30 degrees. So what we're seeing is this is pretty off axis, right? So this is a question that we had before. In general, we assume that the GRBs were looking at them. But in this case, we know that we're actually looking at them from a little bit far away. And this becomes an issue. Like we saw, GRB jets are fairly small, right? The opening angles are not that large. And so what are we actually seeing in this case? Here, going back to the X-ray afterglow. So here what you're seeing is, in all of these are basically going up in increasing frequency along the electromagnetic spectrum. The top left, at the very top, or is it decreasing? Decreasing? Anyway, at the very top left, you have X-ray afterglow. Oh yeah, it must be decreasing. X-ray afterglow, you have some optical, and then you have some, I believe, radio down here. Yeah, so it's decreasing. The diagonal sloping down lines, this is what you would expect from standard fading X-ray emission, standard fading after emission if you're looking on axis. And what you see in X-rays and also later in radio is you see that the afterglow actually seems to be, the emission actually seems to be kind of either flat or maybe rising and then falling over. And so this was an early figure where they said, well, based on the fact that it's off axis, you would expect to see things not fading, you would expect to see them kind of rising. And I'll show a visualization of it later. Oh, right now. I'll show a visualization of that right now. So at the top, this is the visualization we saw before, where in this case, there's the GRB jet. Observe on the bottom, you still have the observers that's grayed out to the side, right? And so what you're going to see over here is how the viewing angle being on versus off axis affects what you see in the afterglow. There's a little bit of a plotting kind of error in the bottom one. But hopefully it'll be understood. Right, so as you're seeing in the bottom one, there's a plotting artifact, but in the bottom one, if you're off axis, at first your viewing angle doesn't, or the amount of what you can see does not actually cover the jet, or it only covers part of the jet maybe. It's only at later times when you get more and more of the jet, and so that's why if you're off axis, you start off not seeing anything or seeing very little, and it's only later that you see some of the jet, you see more of the emission. And then again, because things are fading and stuff, and the viewing, because things are fading and you no longer are increasing your viewing area, then that starts to fade again. So it becomes the question of, all right, we know it's off axis. What does this mean about? So the sort of zero toy model is that it's a uniform, or what we call top hat jet, where in this case you assume that the jet just has one property along the entire viewing angle, let's say, within a certain size, every form along the size. The slightly more realistic models is maybe instead, and it's sort of understandable. What this means is the jet, the Bulk-Lorentz factor, let's say. So the Bulk-Lorentz factor jet is highest in the center, and then it gets smaller as you go farther out. And that is that's something that just sort of makes sense from first principles, that you would expect the highest energy to be right in the middle, and then as you go farther out, things kind of are less and less energetic. The other possibility, instead of actually seeing the sort of the sides of the structure jet, maybe what we're seeing is this other thing called cocoon. What happens in this scenario is that you have a jet and it's plowing through, and then the sides of the jet are starting to interact, let's say, either leftover material or maybe some matter that was spewed out before merger or right after merger. So if it's starting to interfere or starting to interact with that matter, it's going to heat up whatever's around it. As it's heating up whatever's around it, is going to form this what's called a cocoon, and it's going to heat up that material. That material is going to then radiate. And this is say, all right, well, what's the difference between the structure jet and the cocoon model? The difference is that in this case, in the structure jet model, everything is still moving along like a jet, right? Everything is still moving along really relativistically. In the cocoon model, the jet is moving relativistically. The cocoon is sort of expanding sort of more slowly. And so what ends up happening, and you at later times. So this is something that's really important to not only observe GRBs early, but also observe them much later, because at later times, maybe the emission will look different depending on what your model is. So here are a time of events. I stole this from someone else's presentation because I thought they were good and I didn't want to redo his work. Once these slides are online, if you click on one of these links, you'll see all of the slides. Most of the presentations are posted online if you want to see more details. So can you actually? Yeah, you kind of see this. All right, so this is a timeline of the events that happened. So 16 seconds after let's say the GW detection, we had the seconds after the GRB went off. What you're seeing here is a notice. These are the automated notices that come down from the spacecraft. When the spacecraft detects something, it says, I saw something over there. There's a 16-second delay. Part of that is the sort of onboard algorithm has to calculate that localization in the first place and that detection. And part of it is just your spacecraft is over there. It takes a little bit of time to relay the information and then to get that to your servers. So 16 seconds afterwards, there was an automated alert. And then, the 16 seconds is for is the actual detection, and 27 seconds is the onboard localization. 45 minutes later, LIGO reported the coincident detection. This took a little while because, again, it wasn't, this could have been a lot sooner, right? It didn't have to be 45 minutes. It could be sooner if both Hanford and Livingston detected things automatically. If both the automatic pipelines detected things simultaneously, then we say, oh, there was detection here. We're pretty sure it's a real event. And so therefore, we're going to send out a notice immediately, let's say, or we're going to send out alert to the community. The problem was, again, Livingston had that one spike, that one detector disturbance in the middle. And so it took a little bit of sort of humans being in the loop enough to report the detection of this gravitational wave. About 5 hours later, and again, about 5 hours later, we got a joint LIGO-Virgo sky map. This took a little bit of time because first, the instrumental disturbance from Livingston, and you have to do it carefully because it's right in the middle of your signal. If you don't subtract it out properly, you're going to affect the reconstruction of your signal. If you're trying to figure out exactly where your signal is coming from, you want to figure out the instrument disturbance. And so therefore, this took about 5 hours to finally get this information out of exactly where to look in the sky. About 12 hours later, a bunch of optical telescopes they looked at certain parts of the sky and they discovered there's this one galaxy that has a blue optical transient. So there's something new there. It's something fairly blue, and it's something that's consistent with what we'd expect from a kilonova at early times. So the optical telescopes know where to look. As the contours in the sky from gravitational waves and gamma rays, they're pretty big. Optical telescopes can only look at a small portion of the sky, and also a lot of telescopes and things like that only look at a small portion of the sky. So you have to get kind of clever with these. And one thing that people do is they say, all right, we know based on the LIGO observations that it came from this part of the sky and maybe this distance from us. What galaxies do we know of that are in this box? And so what they do is they do galaxy targeting. They say, what galaxies do we know at? We're going to point our telescope at those galaxies and see what's happening at those galaxies. And when they did that, they found that this particular galaxy was one of sort of the brightest and more massive galaxies in the sky. And they find this. Another problem with optical telescopes on the ground is that you have to worry about the sun. If you're an optical astronomer, the sun is really, if you're an X-ray astronomer, the sun is also rays, it's fine. A lot of these places had to wait until the sun went down before they can actually detect things. About 13 hours later, so we saw a little bit before some of these X-ray afterglows. So from the Swift Observatory. Swift also has UV and optical telescope. And Swift also confirmed that there was a fading bright UV source, but at the same time, there was no X-ray emission, so there was no X-ray afterglow. 14 years later, another X-ray observatory, NuSTAR, also confirmed there's no X-ray emission from here. So this is where things started to get a little bit weird, that there's no X-ray emission when we would expect it from something so close to us. 2 days later, Chandra, which is, I think, probably the most sensitive X-ray telescope, and it's also, again, one of these telescopes that is really hard to get time on, looked and also confirmed there was no X-ray emission. So now we are pretty sure there's nothing in X-rays, and that's really weird. 5 days later, Hubble is looking at it, and it detects. So before the previous optical detections were kind of blue, and now Hubble says we're detecting something that's slowly reddening. So consistent with expectations of what's going to happen with the kilonova, it's going to start off blue and red. 9 days later, Chandra, which again is the sort of most sensitive X-ray telescope, revealed that they did evidence X-ray emission from. Finally, get radio emission. So the radio detection occurs about 16 days later. And now this is when people started modeling and putting together data points. Because before, each person only had, or each instrument only, that's it. But now we have enough data points to start to fit a line. And I mean, 2 points is all you need to fit a line. Something fancy or do something curved and try to figure out what's going on with your spectrum, then you need more data points than that. At 100 days, after 100 days, when you combine the optical and optical observations by Hubble, the X-ray observations by Chandra, what you see is that the afterglow is slowly starting to rise. And what they're showing here is that everything is rising, and it might be falling over, but it's not quite certain, because you can see the sort of the contours get really wide at later times, because based on the data, we can't constrain what's exactly going on there. Is it flattening or is it falling? And so on the left, you're seeing, you're just seeing the data points from different, a different X-ray versus different instruments. And then they're all rising and might be falling off, but it's uncertain. At 135 days, that's when you really start to get, when people are really starting to see a plateau in the X-rays. So this is different from the plateaus I was talking about before, right? Before the behavior was steep, shallow, all. But now behavior is kind of rising and then sort of plateauing, and then what's going to happen after that is some sort of turnover and a falling phase. And at 150 days, they saw that the radio was starting to fall down a little bit. So seeing that the radio is falling over at 150 days. At 220 days, the points definitely falling over at this point. So this starts to really help you constrain your viewing angle and the size of the jet and things like that. And at 230 days, they were able to so they followed the radio, right? So they followed the radio emission. And at, let's say, 75 days, they saw the radio emission was coming from this part of the sky. At 230 days, they saw this part of the sky. And so then you can do some calculations to say, how fast is this moving? And so I'm going to talk about that next and what that means for your models and such. And then under 60 days, basically, they had enough data points to really constrain things. So we were discussing before, is it a structured jet? Is it cocoon emission? Late times, whether your emission is coming from jetted material, so relativistic, versus cocoon, so sort of more slowly expanding, that's going to affect the behavior at very late times. And so what this is starting to say is that at 260 days afterwards, that the cocoon is starting to be ruled out at late times. So this is fun. The late-time radio imaging. So what you're seeing, these are the actual radio images. And on the right, this is sort of the contours of these images, or where the signal to noise is placed. At day 75, this is the black set of black curves. At day 230, these are the orange curves. And what they're saying is that based on this, seem to be undergoing superluminal motion, or that it's sort of moving faster than the speed of light. We know that's not true, but let's talk a little bit more about why geometry makes us think that this is true. You can do some sort of simple math. The difference here, if you just read off, the difference here is about 3 milliarc seconds, let's say. So 3 milliarc seconds, that's, if you do the numbers, it's about 10 to the negative 8 radians. The distance we know is about 40 megaparsecs away. So we know that the distance is 40 megaparsecs away and that the angle that's subtended by this motion is 3 milliarc seconds. What's the physical distance that the jet seemed to move? And the physical distance is about 10 to the 16 meters. Now you know it moved this much over 155 days. So you take 10 to the 16 meters divided by 155 days and you get 10 to the 9 meters per second, which is much larger than the speed of light. But this is really a geometric effect. If you have something that's like relativistic beaming and things like that, you have something that's moving relativistically, right? So it's moving relativistically. I guess I should draw. Basically, at a small angle to the observer. So let's see, here is your jet, here is your observer, here it is an eyeball. So you see, so the observer sees over here. At this time, the jet over here is emitting photons in some directions, usually, just along the line of sight. So at this time, the jet emits a photon over here, and it travels along this. The jet itself is traveling at nearly the speed of the photon because it's very relativistic. So the jet is traveling at nearly the speed of the photon. So the photon's going to obviously be faster, and also the jet's at a slight angles, right? So the photon kind of travels like this. The jet travels like this. At some point, the photon that was emitted initially is over here. The jet emits another photon over here. Now, if you compare this, it looks like, and then this photon shows up first. This photon shows up later. So you have the time of arrivals, but it looks like that there's not much, that it looks like the jet moved from this place to this place. So it looked like the jet moved this much in this period of time, when actually what happened was this first photon was emitted earlier. And so this in the relativistic jets of active galactic nuclei. We also saw this in this jet. And so this sort of, with these, if you model very carefully what you expect the emission to like to constrain, I think from here, from these models, the jet was less than, the jet was probably less than, I think about 0.1 radians is how the radio, and then the off-axis, the was again about 0.3 radians. I don't know how many degrees that is. How many degrees is 0.1 radians? I don't remember. We can do some math. All right, we can do math. All right, 0.1 radians times pi radians in 180. So this is around 60.1 degrees-ish. So the angle of the jet was around 6 degrees. This is consistent with what we've seen from other short beams. They seem to be somewhere between a few, less than 10 degrees. So let's see. Now the question is, what was left behind? So that's from the electromagnetic observations. What was left behind? Because we know two neutron stars merge. Okay, we're going to say two neutron stars merge. In any case, something happens where two compact objects merge and you end up, let's say, either a black disk or a massive neutron star or magnetar. So in this case, what was it that was left behind? So from the GRB point of view, this is the central engine, right? This is the thing in the center that produces the sort of energetic emission. From a wave point of view, this is the post, because literally after your objects merge. And so the interesting thing is, if you collapse something, if the two objects merge and collapse into a black hole immediately, you get maybe a little bit of emission after that, but a gravitational wave emission after that, but very quickly the gravitational wave emission drops off and you don't expect to detect anything more. If you have a neutron star, it's a very sort of bumpy, wobbly, asymmetric neutron star, very turbulent neutron star because it just formed from two merging objects. And if you have a neutron star left over, bumpy and wavy, well, how do we get gravitational wave? We get it when you have something that's slightly asymmetric, when you have a changing mass quadrupole moment. When things are slightly asymmetric, and let's say it's around, it's accelerating, then you get gravitational waves. So if you have a lumpy neutron star, you have something that's slightly asymmetric, it's rotating, it's accelerating, it's going to emit gravitational waves. Because there's this question of what remains behind. And again, right, your central engine, W standpoint, what's the post-merger remnant? Then you can start to play this game and say, well, can we actually look for this long wave remnant signal, and can we actually find? So again, assuming that you have two neutron stars, what can you get at the ends? You can get a black hole accretion disk. You can have a sort of forever stable star, or a situation in the middle where first you have a neutron star and then it collapses. The question is, does it collapse immediately, in which you have a hypermassive neutron star? Or does it collapse after maybe minutes or hours, in which case you have a supermassive neutron star or supramassive neutron star? If you notice the minutes and hours, this is also the time scale for the plateaus in the X-ray afterglow. So this is one of the models for the to explain sort of the plateaus and the flares in the X-ray afterglow. Is maybe you have a supramassive neutron star that's hanging out for a while and still emitting energy over minutes and hours. Yeah, that's what I was going to say there. Let's see. So here is a model or a simulation of what might happen when the two neutron stars merge, and you see this is sort of in time, and you have material being kicked out, matter being kicked out, and at around 30 milliseconds, it's collapsed into a black hole. Now, this time scale is only one model of what might have happened. This time scale really depends on things like the neutron star equation state. Well, first of all, it depends on how massive the two neutron stars were originally. If they were both really massive, then it's going to be a lot harder to sustain a sort of a long-lived neutron star after they merge. If they're both really light, then you could get a long-lived neutron star afterwards without having to game playing with the equations of state. There's a lot of range your equation of state is and sort of how squishy or how not squishy stars are. You could get very different behaviors of resonance. So, okay, this is sort of just showing, again, how heavy was the total object left behind. This is around masses. What does that mean? Well, at that point, we have to start to look at what the different equations of state predict. These are very busy plots. So let's just focus on one of them. Let's focus on the one on the left. On the one on the left, you have on the horizontal axis the mass of the primary neutron star. You're seeing here is this term MB static. Non-rotating, right? Yeah, non-rotating can get before it collapses. If something is rotating, and if it's rotating really fast, that can support heavier masses. Sort of, I guess, depending on how you want to look at it, when things are rotating faster, the matter is sort of supported by, let's say, centrifugal forces. This is like when you're on one of those carnival rides, right? And it's rotating really fast, and then you're on the edge, and it's spinning, and then the floor drops, but you're still spinning, right? Because you feel like you're being pushed out. In a similar way, a neutron star has this kind of outward pushing. I don't want to say it's not. Has this sort of behavior, right? Where you actually get the sustain. You can actually sustain heavier masses because they're sort of pushed outward a little or bulged outward. Left-hand side, this is comparing what the equations of state predict to how heavy a non-rotating neutron star can be before it collapses. What are we looking at? All right, all of these different diagonal lines with different colors, these are different equations of states. What this says is anything that's on the left of that line, that means the mass is lower than the mass than how heavy a non-rotating neutron star can get before it collapses. Anything to the left means that it could very well have been a stable neutron star. Anything to the right means that it's heavier than the heaviest a neutron star can be before it collapses if it's not in a row. All right, I'm going to assume it makes sense. If you have questions, we can later. So all of these, so each of these equations of state you can see have different predictions. This curve, this blue and red curve, this is what you get when you look at the gravitational wave data, and this constrains what the actual masses are. If you look, this blue and red curve, it's sort of to the right of most of these equations of state. So this is that based on these equations of state, it probably was not, the mass was probably, what's left over, probably not a stable, non-rotating neutron star. I guess not non-rotating. It wasn't a stable neutron star, shall we say. It wasn't a neutron star that survived forever. All right, the more interesting one is the set of plots on the right. Here, instead of comparing it to how heavy a neutron star can get if it's not rotating, we're comparing how heavy a neutron star can get if it's uniformly rotating. This is the supramassive neutron star. This is the scenario where the neutron star can survive for minutes or hours before it collapses, before it slows down and collapses. This is that sort of, you can interpret this in the same way as you interpret the one on the left. The different diagonal, dotted, or colored lines are for different equations of states. Anything on the right means probably that it's heavier than the neutron star can be if it's uniformly rotating. Anything on the left means that it's lighter and that it can be sort of supported as a supermassive neutron star. What you'll notice is that now sort of half of these or a third of these equations of state are kind of on the right of this. I should slow down. So let's look at the blue and red curve. This is where we think the masses of the two neutron stars are. They lie somewhere on these contours. If you look at so we have these contours, and if you look at the diagonal lines on the right, the black line and the blue line, this is saying that if these are the true equations of states, if these are the correct equations of states, based on these measurements, this neutron star could have been perfectly fine supramassive neutron star. If you notice that the ones on the other dots, or the other diagonal lines, let's look at the pink one. This shows up to the left of this blue and red curve. It says if you believe that this pink equation of state is the correct one, then it could not have been a supramassive neutron star. It had to have been heavier than that, maybe a hypermassive neutron star, which collapses within a milliseconds or less than a second. So depending on the two scenarios, right, you could have a long-lived star that's very bulky that emits gravitational over a longer period of time. So what you can do is you can say, what happens if it's a hypermassive neutron star? So what I'm showing here is some plots of what showed up, or comparing the of that search for a long-lived signal, for a signal within 1 second of trigger, with some expected with some simulations that show what we look like. So in the blue shaded region, sort of the upper limits, right? Because we looked, or LIGO, the collaboration looked for this signal of a hypermassive neutron in gravitational waves within 1 second of the detection. They said, is there an excess? If there's no excess, can we constrain the upper limit? Can we say the excess must have been less than this amount? The energy must have been less than this amount. And that's what the blue shows. And then all these curves down here, the individual curves, these are just taking sort of different signal models and different equations of state and such. What do we expect the spectrum would have looked like? As you can see that the expected spectrum, all these, it's still orders of magnitude below the upper limits. So this kind of shows that for a system like this at this distance, with the current detector sensitivities, you don't get close enough to be able to detect a hypermassive neutron star. Yeah?
Sylvia, in this search, are you guys assuming that it's power in a given frequency, a given set of frequencies, it's not changing over the 1 second?
I have no idea how the search was done. I'm uncertain. But there's a link. It's it's on the archive if you want to take a look at it. So this was sort of a search for a hypermassive neutron star, right? Where you're comparing, and in these scenarios, what you do if you have upper limits is you compare how good are your limits to how sensitive is your detector to how, where you expect your the energy emission to actually be. If you can get your detector to be more sensitive than that, then you can maybe start to detect something. If your detector is not sensitive enough, you're not going to detect anything. This was a search for gravitational wave signals from a supramassive neutron star. So this is one that could last minutes, hours. They went up all the way to 8.5 days just to see if there was any waves. What you're seeing here, this is plotted a little bit differently. So what you're seeing here are the LIGO frequencies, different sets of colored data points. These are the upper limits for just different pipelines, different ways of searching for this signal. On the vertical axis is the upper limit on how far away this event would have had to be for us to detect something. If something's closer to us, then obviously something's closer to us, we have a better chance of detecting it because it's closer, right? If the strain goes down as 1 over, it needs to be close to us in order for us to detect it. This actual event was at around 40 megaparsecs, so that's the dotted line at the very top. We would have only been able to detect a post-merger remnant from a post-merger long-lived signal from this it existed. We would only be able to detect it if the event had been about 1 megaparsec away from us. So this is another way of saying instead of detectors, we're not detect the gravitational wave emission from a post-merger remnant, unfortunately. So this might be something for future detectors. And this is an example of something where people looked at future detectors. So you have LIGO right now. You have advanced LIGO. You have some grades to get to the best you can do with advanced LIGO. Then you have future detectors like the Einstein scope or the Cosmic Explorer. I think decades, half a century away. I don't know, depending on how it goes and politics go. On average, arm lengths, and these are, and they also use different ways to try to lower noise. Because what you're doing is you're detecting very small changes in space-time, right? So you really have to get your background as low as possible, and so there are different ways to do that. Sometimes some of these, I think, go crazy because if you have at room temperature, right? Everything, there's Brownian motion. At room temperature, everything has like a slight random motion associated with it. If you go to lower temperatures and cryogenic temperatures, you really reduce that noise, for instance, on all of your detectors. You can also go underground, where you might get rid of or you lower your seismic noise, because any movement on the Earth will affect your detectors and things like that. Oh, this was fun. Recently, one of the LIGO detectors, weird instrumental glitch, instrumental disturbance that had this weird pattern, turns out ravens. Because what was happening was around the detectors, there was this and the birds were trying to get there to get water. For some reason, I don't know exactly the details, but basically they looked and they said, oh, this looks like ravens. The ravens are pecking here. And they actually had a grad student go out there, the ravens, and pretend to peck there. They looked at what the result was when the grad student poked at it and compared it to the original, and they said, yeah, it's going to be ravens. So that was interesting. That's one of the things when you work on a very sensitive detector. This is tying together a little bit this whole idea of the GRB engine being related to the post-merger remnants. This is going back to the plateaus. What's causing the plateaus in the X-ray afterglows? Is it long-lived, very massive, very highly magnetized neutron star? So what you can do in that case is you look at your X-ray afterglow light curve. So the vertical axis is luminosity, or how much energy is emitted over time, and your time since the GRB began. So this is the light curve where things are kind of dropping and then stabilizing, then dropping again. So you say, well, this particular light curve, let's say, the plateau lasted for about 10 to the 4 seconds. And in that 10 to the 4 seconds, if it was releasing about 10 to the 47 ergs per second, then it must have released a total of 10 to the 51 ergs must have been released in this time. You work backwards and you say, with that 10 to 51 ergs, was the amount of energy that was emitted electromagnetically? Can we say something about how much energy or luminosity was then available to be emitted in gravity? And from there, you can kind of constrain how good you can do with current detectors and future detectors. But this is all sort of looking towards the future and seeing what we can do then. And yeah, so there was a question yesterday about, well, how normal, I discussed a little yesterday, how normal, how weird was this year? How much time do I have? Do I have a lot more time? When did I start? Time. When did I start? 15 past? So this goes to 30 past, yeah? Okay, I have a lot more time. I'm ahead of schedule. So this new GRB, 1708, 17A's twin. Because the problem is, right, you've seen one GRB, you notice all the light curves look different. You see one GRB, how much can you extrapolate from one GRB to say, to inform you about the whole GRB population? So what you have to do, one thing you can do is you can do studies of just one individual GRB. You can also do studies of a whole family or subset of GRBs that have similar properties. So one thing we found, so this is going back to 1708, 17A. So on the right, you see the light curve. These are split into the two energy ranges. The bottom light curve is lower energy. Oh yeah, the bottom light curve goes from 12 to 290 keV, so it goes in this energy range. The top light curve only does 50 to 298 keV, so it's sort of this energy range. So the top is sort of plotting a subset of the bottom. What you see is that there's a peak at 0 across the entire energy range, and then before 2 seconds, there's sort of this excess bump, this sort of soft tail. So this is the hard peak, the soft tail. We talked about how hard just means that it's sort of it's the non-thermal equivalent to hotter, I guess, the higher energy. And on the left, what I'm plotting is the spectrum. And so the green is the spectrum of the main peak, which is sort of this kind of this smoothly broken power law, kind of this broad spectrum. And then the purple is the soft tail, which is sort of steeper, and this just looks more like a black body. So when they looked back in the data, they found this other 1501B. This one was much farther away. This was about 10 times farther away. It was at 500 megaparsecs instead of 40 megaparsecs. And again, you see a higher energy non-thermal spike and then a lower energy thermal tail that lasts a little bit. The timescales are a little bit different. But so what you're seeing here, again, is the light plotted in different energy bands. The very bottom is the lowest energy, and then the medium energy, and then the highest energy. So you can see if you go to the highest energy, all you see is that initial spike goes to the emission lasts for longer. And so again, you have this short high energy, non-thermal spike, and then a lower energy, longer tail. Are very pretty plots that they started to use to demonstrate what these GRBs look like. So in all of these, let's see, what are we looking at? Let's look at the one on the, it doesn't matter. In both of these plots, what you have on the horizontal axis is time, and on the right, what this is showing you is what happens if you bin your data. Because what you're doing is you're trying to take the spectrum, right? So you're trying to see what the spectrum looks like. But you can't just do that. I mean, you could do it instantaneously if we had really good detectors. What we do is we say, in this 0.1 seconds, what did the spectrum look like? Within this 0.2 seconds, what did the spectrum look like? Within this 1 second. So the thing is, when you take the longer durations, you have more photons, so you can do better by fitting your spectrum. But if you're changing really rapidly, then maybe you also have spectral evolution. And so the danger is if you take longer time durations, then you have more photons, you have more signal, but maybe you're smearing individual peaks. If you take less, really capturing what's going on in the GRB at that time, spectrum. So what they're showing is at the very bottom, this horizontal row is what happens if you take bins of sort of 0.04 seconds. And then at the very top, this is taking a whole half-second bin. So what's showing is what happens if you take the spectra in small bins and then it's a successfully longer bin. So you can kind of see what does the spectrum look like overall, as well as what's happening at short times, at shots. The different colors. Blue, so blue is just the hard spectrum, very sort of high energy spectrum. In green, it's sort of normally what we see for short GRBs. In red is softer, it's sort of lower energy kind of spectrum. And then in purple is very soft. And this is something that I think sort of, you don't see in many GRBs, but that we've seen in the past from some other things. And so in both of these cases, so on the left you have 150101B, on the right you have 1708, 17A. These kind of look like twins because just by looking at these, you can see there's the green at the beginning and then there's the purple at the end. So maybe when I showed you, you didn't quite believe me, right? Like the green over here really an actual detection, right? Is this really just a tail? Was this a tail or was this just kind of detector fluctuations? Data. They fit the data and they say, does it look like this could actually, is this actually a significant spectrum that explains well the the data at this time. They do that. They saw that yes, there are these other GRBs that have this short hard spike or the sort of normal spectrum, and then they had this long tail afterwards. That's sort of this thermal. Yeah. The, right after 2 seconds. Yeah, I mean, so yeah, that's the thing. Game where, right, because if background dominated, you could play this game where it's not immediately apparent why things, if things are actually interesting or not. I guess the answer is if you look, right, if you just look at the light curves, it's not obvious to the human eye, right? We're really good at finding patterns. It's if you look, then you do the spectral analysis. When you do the spectral analysis, it turns out that it seems like there's not much. Oh, I see what you're saying, that maybe there's something at. It's a combination of things. So, okay, so here's one way, so this whole thing of duration and stuff like that. Here's what actually happens when you do GBM data analysis. So you have this GRB, and it shows up, and it sort of looks like this maybe, or it looks like that, or something like that, and then there's sort of background. But the problem is your background isn't beautiful and flat. It's got all these fluctuations, right? So this is sort of the issue I was saying before of how do you determine your timescales? How do you know your GRB is this short versus this short versus this short, right? And this is sort of dependent also on your background level. What you can do is, yes, let me think. So what you do is you make different assumptions about what the background is. It could look like this, or you could say it looks like this, or maybe maybe over here does this, you say the background actually looks like this. What you do is you do the best you can to fit the backgrounds based on what's going on before the burst and after the burst, and you sort of extrapolate, because you expect the background to be changing very slowly. The background is the particle background. The rate of the particle background only depends on where you are in the sky, because of the Earth's magnetic fields and things like that. These are all background fluctuations because sometimes you'll detect a particle, sometimes you won't. Sometimes you'll hit something, sometimes you won't. But the rate itself is changing very slowly for the most part. So you assume some background rate you do the best you can based on what's going on before and after the burst. Then what you do is you take that and you take what's left over and you draw a cumulative. When you draw a cumulative light curve, normally what you see for this burst, you might see something like this. Before the burst begins, maybe there's fluctuations, stuff like that, but it should sort of sort out around 0, right? Because you have positive fluctuations, you also have negative. When you get this first peak, then all of a sudden the rate increases really quickly. There's nothing here, the rate drops, the rate steadies again, and then you get this another peak, and the rate goes like this. And then what you do is you say, so for GRBs, we don't report the total duration because that's not very well defined. We report T90. So T90 is what is the time scale in which the central 90% of the emission was detected. So if this is 90%, then we say it's this time to this time. And so then your question goes back to, how do we know if there's sort of not something over here? Because what you do is you can try a bunch of different background fits, and you do the best you can with the background. At some point, this just levels off. If this just levels off, and this just levels off, then that tells you then basically your GRB is contained within intervals. And so when you do that, you find that these sort of fluctuations afterwards, which by eye look like they could be interesting, and also the fluctuations before that, you find out that mathematically these fluctuations all average out to be 0.
Some people run back and forth saying that a third of GRBs were showing this long-term emission. Because now the work, all of them would show it?
It's tricky at this point because we only have 2 GRBs so far that look like this in particular. So the thing that Luis is mentioning, so there's long GRBs, that's fine. There's short GRBs, that's fine. There's also some that kind of look in between. Some that have sort of GRBs that, if you look at them, they look short, but then there's sort of this long kind of emission. So this sort of GRB was known before 1708-17, before all of this happened. The thing is, this time scale, usually, so let's say, usually this is like, let's say 2 seconds long. This was usually around, I don't know, tens of seconds. This was much longer. Could have been maybe up to a minute and something like that. This also was usually lower energy, but I'm not sure it was necessarily thermal emission. So it wasn't necessarily exactly the same as what we're seeing in these GRBs here. But it, right? And we're seeing peak with some long. The problem is we use this word long to describe many different things, right? We're describing a long tail of maybe, I don't know, 0.1 seconds. We're also describing a long tail of 60 seconds. It's possible that these are, it's unclear right now whether they're the same thing. I would say things, so this is what you have to do with GRB data analysis, right? You have to get as much information as you can, the spectral features, about the temporal features, and also how the spectral features are changing over time. The energy over time, is the energy, getting lower and lower, or are there new spikes and new energy injections, things like that. So it's possible, if you look at, kind of spitballing a little bit here, there's lots of literature that has done this before, or has done this already. It's possible that if you look at this these are what's known as the short GRB with extended emission. So this is a subset of bursts that interesting thing. So going back to this whole issue of what's your duration? Maybe your duration will depend on your background level, the duration you measure. The duration will also depend on your energy range, right? So there are two detectors that are sort of interesting here. So the GBM detects things at slightly high energies. There's also the Swift gamma ray, the Swift burst alert transient monitor that detects things at slightly lower energies. If you look at a burst like this, the short GRB with extended emission, if you look in the GBM, all you see is the peak. If you look at it with Swift, you actually see everything. This is much lower energy emission than what the GBM can see. And so, what was I going with? Yeah, so it's possible. So the other thing is that Swift, the GBM monitor on Swift has a much smaller field of view. The gamma ray burst monitor, the GBM monitor, the gamma ray burst monitor on Fermi can see the entire sky at all times. The burst alert telescope, burst and transient telescope, the BAT on Swift, which is what detects GRBs on Swift, only has a much smaller field of view. Swift does not see all the GRBs that GBM sees just because it's looking at a much smaller part. So then again, you have to disentangle these instrumental effects, these observational biases from maybe all GRBs, maybe all short GRBs have this, and maybe we're not seeing this for a lot of short GRBs because the energies aren't right. Maybe we're seeing it for these couple of GRBs. So, maybe these are closer on average, or maybe there's something special happening there. Yeah, so happening, said it all. And so the obvious thing to do will be to look in optical and X-ray emission for this GRB, and that's what people did. So this is 1708-17A's twin, maybe. What you're seeing, let's see, on the left-hand side, this is the X-ray afterglow. Yeah, this is the X-ray detections. In red, in blue, at the very top, this is the optical transient or the optical excess associated with 1708-17A, because it says 2017 up there. In red, this is the X-ray excess. Wait, that's a little bit confusing. No, sorry, this is still optical. This is the optical excess that they found for this new GRB that happened in 2015. So what they're seeing here is that, all right, the behavior is a little bit hard to constrain at this point, but it's kind of similar. It's kind of similar in both cases, and you're seeing this on you're seeing this on the right-hand plot as well, is that the behavior in X-rays, sort of the extrapolated behavior in X-rays, is also very similar in both cases. So this is another way of saying that maybe these two things are related, but more studies need to be done. Unfortunately, this one happened in 2015, so anything you can see is really faded right now. But it's an important case study to show that in the future, it happened 3 years ago, in the future there might be other GRBs that are similar to this, and maybe we should be looking at short GRBs a lot more carefully than we are. And I think, that's all I have. We still have 20 minutes. Who has questions? What do we want to talk about? Wait, how much time? We don't have time. No, sorry. When did we bad at math? 5 minutes? Do we have 5 minutes? What time is this supposed to end? Oh, I'm really sorry. We are 10 minutes behind. Okay,